Hello all, this is Mr. G and this is our warm-up for today's lesson. So pause the video right here, give this problem a shot, come back when you think you have an answer. We're going over in 3, 2, 1, let's go. So they're giving us a function h of t equals negative 16t squared plus 20t plus 2 that represents the height of some projectile. So let's plug that into our graphic calculator. Negative 16x squared plus 20x plus 2. And then I'm going to hit graph. And there's our parabola. Okay, now when will the projectile reach its maximum height? So A is asking about the maximum, so I hit second to calculate maximum, which is number 4. Then I do my left bound, right bound, hit enter to the left of the maximum, move to the right of the maximum. That's a little bit farther than I needed to go, but whatever. Enter one more time to guess, and it gives us the maximum value of 0.625 and 8.25. But they're asking us when will the projectile reach its maximum height? So they're asking about time. Well, time is on the x-axis here, so that would be at 0.625 seconds. That's when it would reach its maximum height. Okay, next thing it says is when will the projectile hit the ground? So when it hits the ground, that's when its height is 0, so that's a real root. So I have to hit second, calculate, hit number 2 for 0, which is the x-intercept, which is the real root. Then I've got to do left bound, right bound around my real root. I'm going to hit enter to the left of it, move to the right of it, hit enter and enter one more time. And then it gives us 1.34 seconds and negative 1 e negative 12. Remember, anytime it says e and a negative number, that means 0. So the y value is essentially 0. So again, it's asking for when it will hit the ground. That's the x value. So that will be after 1.34 seconds. 1.34 seconds. And last but not least, it says, what is the projectile's starting height? Well, the starting height is just the y-intercept. So the y-intercept is always the c value. So we can just say the starting height is 2 feet. Now, if you ever forget that the starting height is the y-intercept, which is always the c value, you can just think, okay, well, the starting height, that would be an x value of 0. So we can hit second, calculate value, type in 0 for x, and hit enter, and there you go. It gives you 0, 2. So the y value, the height, is 2 when we're starting. So there's our warm-up. Let's take a look at the objective. Today we're doing chapter 4, section 9, and after today we should be able to find real solutions to systems that include quadratics. So systems hopefully sounds kind of familiar. That's something we did back in chapter 3. I actually really like this section, 4-9, because it's really a connection between the two chapters we've done. In chapter 3, it was all about systems, and chapter 4 is all about quadratics. And in this this section, we're going to see systems that have quadratics in it. So let's sort of pull some information back to the front of our brain. So what methods do we know to help us solve systems? So if we have a system, like say we had x equals 7 plus 2y, and then, I don't know, 3y minus x equals 11. I'm just making these numbers up. If we had a system that looks like that, there were a few methods we know how to solve, or we know to solve it, I should say. One was substitution, where we get a variable by itself and substitute its expression that it equals into the other equation. There's the elimination method, where we try to create, find two opposite coefficients in the x's or the y's, and then they'll eliminate, they'll cancel each other out. But there's a third method that we didn't talk about too much because it's not really the most efficient method most of the time, and that's graphing. Like I said, most of the time graphing is not the best way to do it, but if we have a graphing calculator, all of a sudden graphing becomes a much more attractive option. So when we solve by graphing, how do we find the solutions? So once we have our graph, so could be the graph of two linear equations, where would the solution be? Hopefully you remember that the solution would be right there, the point where they're crossing. So essentially what you need to remember is that the solution is the intersection. The solution is the intersection. So keep that in mind as we go through our next slides. So if the solution is the intersection, if we have one linear equation and one quadratic equation, remember quadratics always make a parabola, how many solutions are possible? Well, let's think about this. We could definitely have two solutions, because there they'd be crossing twice, right there and right there. So that's one possibility, two solutions. But it doesn't have to be two solutions, because they could be missing each other entirely. That would be no solutions. And it also could be one solution. They could be touching at just one point. So not even crossing each other, just barely touching each other at that one point. So there's three different possibilities. Could be two solutions, could be one solution, could be zero solutions. That's if there's one linear and one quadratic. But what if we had two quadratic equations? How many solutions would be possible? It is still the same three. It's still two solutions, one solution, and zero solutions. But the way it looks can be a little bit, it can look a little bit different depending on whether if they're both concave up or concave down, or if we have a mixture. So let's talk about when there's a mixture. Let's say we had one concave up and one concave down. Well, it's easy to see how they'd be two solutions. Okay, they're crossing twice there. One solution, they're just barely touching. Doesn't have to be at the vertex, or the vertices rather, but it could be, but just touching one point. Or zero solutions would be no intersections. But what if instead of having one concave up and one concave down, what if they were both concave up? To make that one a little bit wider to make this easier to see. Well, it's easy to see that would be no solutions right there because they're not crossing at all. Two solutions would be two intersections, and one solution would be, again, just barely touching each other at one point. Could be there or over there, or maybe the vertices are touching. Lots of options there. So it could still be two solutions, one solution, or zero solutions. So the first thing we need to do anytime we have a system that contains one or more quadratics is to look at the graph and figure out, okay, how many solutions, at least how many real solutions are we going to expect? Let's take a look at example one. We want to find all real solutions to the following system: y equals x squared plus 3x minus 2, and y equals x minus 5. Let's go to y equals, clear out what we had before, x squared plus 3x minus 2. And when we're typing this in, keep in mind that it is possible to solve these by hand. Like, we could still use a substitution method. Elimination might not be the best way to do it. I would probably, if I was going to solve this by hand, I'd do it by substitution. But solving by graphing with a graphing calculator is going to be so much faster. So x squared plus 3x minus 2 and x minus 5. Here we get graph. And let's see what we're looking at here. There's our quadratic, and there's our linear. Oh, and hopefully right away you're noticing there's no solutions here. At least no real solutions, because there's no intersections. Now, I didn't just put no solutions. I put no real solutions. That's going to be really important. Make sure you include that word real in your answer when you say there's no real solutions. So that's it for example one. All done. Let's take a look at example two. Find all real solutions to this system. So let's plug this in. Most of this is actually identical. So it's still x squared plus 3x minus 2. We just have to change the x minus 5 to an x plus 5. Then we hit graph. There's the quadratic. There's our linear. Now here we see two solutions. This is a situation where they're crossing twice. There's two intersections. So let's go find them. Hopefully you remember how to find an intersection. We go to the calculate menu. So I hit second, calculate, go to 5 for intersect. And let's find the one on the left first. So I'm going to move over. Here you do not have to do left bound, right bound, or any of that. You just move close to it, hit enter for the first curve, enter for the second curve, and enter to guess. And it gives us our first solution of x equals, negative 3.83 when we're at 2, 3.83, and y equals 1.17 it rounds to. So that's our first pair of solutions. X could equal negative 3.83, and y could equal 1.17. I guess technically those should be approximates because I rounded. That's something I almost always forget to do. Okay, now let's find the other one. Second, calculate 5 for intersect. I'm going to hit up so I can move along the linear equation just to make it a little bit faster. It doesn't make a difference though. You can move along the parabola and it'll take a little bit longer, but eventually you'll get there. That's close enough. Enter for first curve, enter for second curve, enter for guess. And it gives us, let's do this in a different color so it stands out. So the second possible solution, or the second solution I should say, the second real solution, there we go, finally got it. X is approximately 1.83. And y is approximately 6.83. Now, if you wanted to, you could write them as an ordered pair, like the first solution. You could have written it as negative 3.83 and 1.17. You could have done that as well, but I like to write it like this, because that sort of emphasizes that we didn't just find an ordered pair. We didn't just find a point. We found an x and a y value that work, that solve this system of equations. Let's take a look at example 3. This one I want you to try on your own. So you got to find all the real solutions to this system. 3, 2, 1. Let's go over the answers. Hit y equals, clear out everything from the last example. The first one is 1 divided by 2x squared plus x plus 1. Okay. Now the second one is x squared plus 6x minus 3. Let me just make sure I missed the 3. Let's make sure I type them in correctly. One have x squared plus x plus 1 and x squared plus 6x minus 3. Very good. Then we hit graph. And let's see what we're looking at. Okay, this is going to be a two-solution problem. I see two intersections, or rather, I see one, but I know the second one's there. Let's find the intersection we can see. So second, calculate intersect. I'm going to move there, hit enter, enter, enter. The first solution, we're going to have to round again. We get x is approximately, what is that, 0.74. And y is approximately, look on the screen here, 2.02. All right, that's our first solution. Now, to find the second solution, it's actually going to be, let me hit trace, just so we're along the line. It's actually going to be further to the left, because moving to the left, eventually those two parabolas are going to cross again. So to hopefully show this, let's see if I can do this quickly. I'm going to zoom out. So zoom out, and I'm going to move over, center my zooming out around there, hit enter. Let's see if we can see this a little bit better. Yeah, now we can see that second intersection. Again, it's not super clear, but we can see where it's going to be. So I'm going to hit second, calculate 5 for intersect, and move closer to the intersection, hit enter, 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 and let's see what we get. We get x is approximately 10.74, wait, negative 10.74, always the sign mistakes get me. Negative 10.74, and y is approximately 47.98. Is that rounds to? 47.98, yeah, very good. Okay, and that's it. We're all done. Hopefully you got those two answers on your own. Here's our homework. I want you to work on page 262 in our algebra textbooks. Do numbers 8 through 13 and 20 through 25. Hopefully this all made sense. As always, if you have questions, let me know. Enjoy the rest of your day.